4k, and that's why it is called fourth order. Okay, 4k values, and based on that you can calculate same way. It goes same way. So please keep that thing in mind. It is not much different. Only thing is that you are doing calculating 4k values, k1, k2, k3, k4. Based on that you are calculating you are calculating y or u at different value of x. Okay, and certainly as you can expect that fourth order will give more accurate result in comparison to second order. Okay, so but this is once you have written a program, it is not very difficult to do. I started with second order because it is difficult to solve ourselves, right? But let me give you one example here. So this is example, du by dx is minus tu 2u plus x plus 4, and this is given initial value of u at x is equal to 0, and that is equal to 1. So they started doing u 0.2 first. They calculate by taking h is equal to 0.2 or delta x in that equation. Then you calculate f, which is nothing but f. This is function of x is 0 and u0 already you know. This is simply, for example, in kinetics this will be concentration at time t is equal to 0. Then all k1, k2, k3, k4 is calculated. It is given value here, and then there is another equation which I told that u 0.2 will be u at 0 plus 1 by 6 multiplied by this multiplied by h value. If you remember here, k1, 2k2, 2k3, k4 into delta x. Delta x is basically h. So you can see this value k1, 2 plus 2 into 1.7, 2 into 1.76 plus 1.496. So this is k1 plus 2, k2 plus 2, k3 plus k4 into h, and this is 1 by 6 multiplied by this and plus. So that will give you value f y is equal to 0.2. And then you can calculate u at 0.4 also. Same way, but then you start with u 0.2. Because now you know what is u at 0.2. Initially you know only u at a particular value, means u when x is equal to 0. So initial concentration generally we know, so we can calculate value of u at 0.2. So fourth order will give more accurate value. So there are two things which is very important. Number of iteration, if you can increase, that will also give you more accurate result. And in place of second order, if you can use the fourth order, that will also give you much better result. Okay, more accurate solution for that. And this I told you about how to solve differential equations. Same thing happens when you are going and trying to solve, root of equation for, like third order or fourth order equations, right? For example, alpha x4 plus beta x3 plus gamma x square plus delta x plus epsilon is equal to 0. That can be solved using computational means using the concept from numerical analysis, and you can write the different means you can write scientific programming for that, and you can solve it. Is this okay? Any question here?
Sir,
Yes.
Through which order can we use this method on?
Means I told you that if you are really interested, one thing is just to learn, and then second order may be good enough. But if you want more accurate result, probably you should go for fourth order.
Okay, okay, sir. Thank you.
Okay, generally people use fourth order. Yeah, certainly then again number of iteration also matters. But fourth order will give more accurate result in comparison to second order.
Right, sir. Thank you.
Okay, any other questions?
Sir, can you please explain that iteration part again, how it is increasing accuracy?
Yeah, so what happens here? I told you that 0.01. Okay, 0.0. Suppose you want to calculate y at x is equal to 0 0.1. Right. If you go in one step, the value you get may not be closer to what the accurate value is. So it is better to use a smaller value of h. Okay. So the same thing can be done in like 10 steps using h is equal to 0.01. So first you will get h as first you will get y at 0.01, then y at 0.02, y at 0.03, y at 0.04, 0.05, and so on. So 10 steps you can do in 10 steps, and the value what you will get will be more accurate in comparison to the value which you got in one step. So that's where iteration comes into picture. Okay, so doing for yourself in 10 step will be very difficult. It will consume lot of time, but for computer it will not take within 2 minutes. It is like the whole thing will be done. All right,
Sir,
but yeah, please.
what will be the error if we do it in one step? Like
It is
what
difficult
percent
to
error?
no, it is difficult to say. Means it is difficult to say. Okay, it will again depend on a lot of things like how complex this equation is. Okay, so there are a lot of things which comes in. So it is very difficult for you to tell. Only thing you can do is you can just simply do two step and then 10 step method and see whether in those two step you are getting almost same result. Then probably you don't need to do a 10 step. So whenever you try to do it, you try to like just simulate first for more than 10 step or more than 100 step, and then you compare with 10 step thing, and then you compare result. Okay, sometimes maybe you don't need to go in 100 step, but that will totally depend on differential equation. Okay, totally depend on differential equations. So please keep in mind it is very difficult to say how many steps you need to take.
Okay, sir.
Okay.
Sir, hello.
Yeah.
Sir, in every iteration, the f naught, x naught, and y naught will change, right? They will assume the value from the last iteration.
Yeah, you are right.
Okay, sir.
Okay. For example, next step, if you take k1 dash, then it will be h if at 0.1. For example, I am going 0.1, 0.2 if I am calculating. All right. Then in that case, this value I have already got. So I will use that value here. So y at 0.1 and x is equal to 0.1. That value I am going to use. All right. That's otherwise there will no advantage. Am I right? You are doing same thing again. You are not going to get anything else. All right. So first you calculate y at 0.1, then y at 0.2 using y at 0.1. In that case, I mean f is equal to f is simply I can write k1 h f at h. then F at 2H, then F at 3H, 4H, 5H, 6H, then 10H. Something like that you have to do, and then you can get more accurate result. Is this okay?
Yes.
It is not very difficult. The only thing, it is a bit, it is time taking, but it is not difficult. And for computer, it is quite like, very easy. Once you wrote the program, it will do itself. It has to just only thing you have to increment H value by 0.1. Okay. So you will see there are, like if you go to library, there are like book like numerical in Fortran, C++. So in fact, this already has been done for all the numerical analysis, equations. Those program has already been developed, and people just simply use from that. But it will be better if you are really interested in doing, like scientific programming. You should know numerical analysis and do yourself, either using these programming methods or MATLAB, Mathematica, anything you can use. And particularly since you are from chemical engineering background, these things will be needed. There are a lot of differential equations and integration you will come across, lot of fitting you have to do, and a lot of modeling you have to do. So if you propose a model, then for example, we propose a model like my gas behaves as van der Waals gas, but then we have to prove it, am I right? Your gas may not behave as van der Waals gas. So you need to get experimental result, and you need to, uh, your model is van der Waals gas model. You try to fit the data to first see whether uh, it really follow your model or not. If not, then you have to think of another model. All right. But for modeling, then you need to do simulation, and you have to match with the experiment. If it matches, then you say, okay, this gas follows van der Waals gas equation. If not, similarly, you will come across several topics where you have to propose a model. But if you propose a model, you need to show also that it matches with the experimental data. If it doesn't match with experimental data, then your model is not right. All right. So please keep this thing in mind. So similarly in kinetics, what people do is, okay, they assume that it is a first order. Suppose it is a first order, then you will have a different dc by dt. If it is a second order, then there will be a different dc by dt. And then you don't need to solve it. What you will get is experimentally you can observe concentration versus time, and then by numerical analysis, you know if it is first order, which kind of equation you will get, and then you fit it. If it fits, then certainly probably your reaction is first order. Otherwise, you need to fit with the different equations. So in fact, you can try to do that. Once you generate data by assuming first order, and then you see numerical analysis karke dekho whether you will. So for example, if I suppose I take minus dA by dt is equal to, sorry, dA by dt is equal to k into A, right? Then you know, okay, initial concentration is this, and then k ki value we suppose pata hai. Then generate experimental data. So sometimes people also do same thing. Okay, experimental data. In fact, you can even add noise. And then by numerical analysis, you try to fit that experimental data which Means you see that you have got from solve this, and after solving this, and then do by numerical analysis try to get the value of k. If you get it, then probably you have written the right right programming. So this is the way people test their programs also. Okay, any other questions here? No question,
No,
then yeah, someone.
no, sir, no question.
Okay, so so this is how you solve differential equations, and in the next lecture probably I will show you how to show you one very nice example where very complex differential equation was obtained, and based on that we can in that you don't have any choice, but you have to solve the differential equation. Okay, so people do that. There are a lot of softwares which is also available, which basically written program for solving differential equation, particularly kinetic equation for different models, and just by looking at the experimental data and fitting with those models, people decide which model your reaction follows. Okay, now next is we have already discussed slow reactions, but how to measure rate of reaction for fast reaction. And this is particularly important for reversible reaction because reversible reactions are very fast. Okay, so it means in 1 minute your reaction is complete, and certainly then you cannot measure rate of reaction because you don't have concentration at different time data. So getting the order of reaction will be difficult. Okay, so the way we that is being done in the lab is shown here. The one method is what is known as continuous flow method. So in continuous flow method, there is like A in this and B in this. Generally, if you are doing dealing with enzyme substrate reaction, then you put in one syringe enzyme and in second syringe substrate, and then you mix it, and then it flows through this. This is the detector. It looks as one physical property, for example, absorbance or fluorescence intensity. Okay, and this is movable. Okay, it can be moved. Okay, so if you measure here, probably you are just after mixing, you are getting the concentration of reactant or product. So it is almost like at time t is equal to 0, or time t is equal to mixing also takes a bit of time. So that time you can say that that is known as dead time. So that at that dead time you can get the concentration of reactant or product. But if you move here, then depending on flow rate and this distance, you can calculate time. So at different time, you can calculate what is the concentration of A or what is the physical property of a reactant or product at this time. You can bring it here, then you can get again flow rate and distance will tell you at what time you are looking at the concentration. Good thing about that we are not worried when I am measuring it. Okay, this time at a time of reaction will be decided by flow rate and this distance, not by when I measure it. I can measure it first here and I can measure at this time. Then I can bring it here and then we can get your concentration of reactant or product at that time. I can measure it 1 hour. Suppose 1 hour this is going on. And if I put it here, I will again get, because you see, this is always a new solution is coming and going down, right? After mixing reaction starts. So whenever I measure, it doesn't matter. I started this thing, suppose I started this thing at 11 and I took measurement at 11:30, it doesn't matter. 11:30 or 11:15, if I am measuring here by bringing this detector here, I'm measuring the concentration of reactant at the dead time. All right. So that is the beauty of this continuous flow method. So syringes are filled with A and B solution and compressed at constant rate. Flow rate must exceed turbulent limit. Age of solution is proportional to flow tube distance. That's what I was talking about, this distance, and flow rate. Okay. So distance divided by flow rate will give you time. Time, so that time will be given here. So distance by flow rate. Only one time point per measurement position. So it doesn't matter when you measure at this point, okay, it will give only 1 point. That is only limited by this distance and the flow rate. What is the disadvantage of this thing is large volumes required, because you are doing it for a long hours. Okay, long hours, and so this solution is going out and that is getting wasted. Right. So that is one of the limitation with this method, but it is very accurate method. Only thing you are worried about is how much you need to have very good mixture, so that dead time of mixing is dead time of mixing is very small. That can be in microsecond. Okay. And then you can measure at different time what is the concentration. Is it clear?
Yes.
Okay. Next method is stop flow method. That is.
So in the previous method, you said that the reaction is very fast. So how will we get the concentration at large time? How did you say that?
Now, what I am saying that you see that mixer is dead time is microsecond, and these all are done by the instrument. You just only need to put enzyme and substrate here, and that thing, like flow. You just decide what is the flow rate, that will be done by this. So you don't have to do anything. In one side you put A and one side B, and then let computer do its own job. And in computer you can decide what is the flow rate in that, and then this will move itself and that will calculate. So one is mixing is very fast, so in microsecond mixing is done. So from that, and this also takes measurement in microsecond region. So in microsecond time you can measure what is the concentration at concentration of reactant or product with time. Okay. Now you see stop flow a bit different in the sense that what they have done, same syringe A and B, you keep it here, it is by measuring fluorescence. But what has been done in this case, that now you stop here. Okay, you stop, put some stopper, and that's what they have done here, put one stopper. Okay, so you are not losing sample. In that case, what you do generally is your this detector is not movable. It is taking at one point. Okay, so it is once it is mixed, then it is, you know, it is just taking measurement at different time interval. So advantage is you are not losing sample, but disadvantage is here your detection should be very fast. You remember at this thing, when I am detecting, it doesn't matter. But here you have to take several very fast, like first measurement, second measurement, third. The gap between two measurements should be very fast, and that is not required in the continuous flow method. I can take after 1 hour, it doesn't matter. Between two measurement gap can be like 10 minutes, but still we will measuring the age which we say age at in microsecond scale. But here you have to take picture or you have to detect it very fast. Between two measurement, the time gap should be very small. Okay, detector is fixed, and we are trying. We just take several picture, but between two measurement, the intervals should be very small. Then we can look at the age at time in millisecond or microsecond. Generally, we get the age at, in millisecond time scale using this method. That requires very expensive detection system. After one photo, the second detection should be done in millisecond, and that limitation is not in the continuous flow. So continuous flow has advantage that you don't need very expensive detective system, but your solution, you require a very large solution. In this, you don't require very large solution. Even with 50 to 200 microliter, this can be done. Only thing that now instruments should be very sensitive, particularly its detection system. And certainly then this instrument will be very costly. Okay, so generally, for example, uh, like enzymes which are very costly, we need to use a stop flow method. So these are the two different ways to look at very fast reactions. But again, this is limited by microsecond to millisecond region. The reaction in which we can take data in microsecond or millisecond time scale. But there are some reactions which is more faster. For example, they will take place only in like 100 nanosecond or something like that. So for that, even these flow methods are not good. But in next lecture, I will discuss what can be done for those kind of reactions. Any questions?
Therefore, but so fir we can say that these both methods are to find the kinetics, how the fast is the reaction. Can we say that?
Yeah, so what we can do is, for example, if we know that our reaction is fast, that you can always know, because in like 1 minute you take, 2 minutes you take the data, and if reaction is complete, you will not see any change, right? So in that case, you know that you are dealing with a very fast reaction. In that case, you don't have any choice but go for this either continuous flow method or stop flow method. Right. Yes. If like a reaction completes in, even in, suppose you are saying that If I do measurement in microsecond or millisecond, still the concentration is not changing. Right? In that case, you will probably think that it is getting completed in less than 1 millisecond or 1 microsecond. Then you have to think of other methods. So it all typically depends on how your reaction is fast or slow.
The continuous flow method can also derive the order of the reaction by moving the detector. Can it?
Means if you measure concentration with time, then it is simply fitting. Main thing is that you have to measure not only concentration, you can measure absorbance versus time or fluorescence intensity with time. And I told you how to use that for calculating. So only thing is this enables you to measure concentration or absorbance when the reaction is not complete. After that, everything is same. You can use integrated rate law. You can use other things.
Okay.
Is this okay?
Yes.
Rohit?
Yes, sir.
Okay.
Sir,
Okay.
like the stop flow method example is the costly enzyme. So, is there any specific example for continuous flow method?
Yeah, there are a lot of means I have to find out reaction, particularly, for example, uh, water dissociation happens in nanosecond. Right. So for microsecond, I have to find out a thing. Okay. Because generally, I work with proteins, and so uh, I know that we generally use a stop flow method for that. But for continuous flow, sorry, I don't remember any reactions.
Okay, sir.
But I can find out and let you know.
Say, what this line means, detector sees more than one edge.
Detector, what?
The third line of this slide. Yes, sir.
Detector see more than one edge. Okay. So what I mean is that you can take at 1 microsecond, suppose you take. So your data is 1 millisecond, suppose you take. So data is 1 millisecond, then after 1 millisecond, you can see two detector. When you fix detector, it is going to see all the edges. Edges means what is the concentration, what is the absorbance, suppose you have absorbance detector. So it is also seeing at 1 millisecond, 2 millisecond, 3 millisecond. You can see more than one edges without moving. Here I mean without moving. Okay. In the continuous flow method, if you don't move, it is going to see one edge only. Okay. In this, if I am not moving this detector, then I am going to see only one edge, because edge is limited by this distance and flow rate. Right. If I move, then I can see more than one edges. But in this, just with a fixed detector, I can see more than one edges. Is it clear?
Yes, sir.
Okay. So tomorrow I will not be in IIT. I will try to get connected to you wherever I am going. And but if suppose I am not able to connect, then probably we have to prepone it. But please come at that time. I will try to connect to you at 12. All right. If I am able to connect, then I will take class. If I am not able to connect, then probably we will postpone the class. Is it okay?
Okay, sir.
Yes, sir.
This is for tomorrow.
Okay, sir.
Okay. And again, feel free to ask questions, and you can always write email to me. Okay, so I will stop here.
Thank you, sir.
Thank you, sir.
Thank you.
Thank you.